All right, so I wanted to go over a couple of the solutions to the problems. I'm going to be going over the even problems, the odd problems. You can find the solutions in the back of the textbook. But hopefully you've noticed the way that things work is they essentially have an identical problem, even and odd. So if you can follow along with the solution right here, you should be able to see how it works with the odd problems. All right, so the first one talks about having a half cell with silver in a silver nitrate solution, and it also has nickel in a nickel nitrate solution in the other half cell. All right, so first you got to figure out what's going to be the cathode and what's going to be the anode. All right, so what I would do is let's look over here and see which one between nickel and silver, which one likes being in its metal form. Looks like silver really likes to be in its metal form. Remember, think about things like gold, it likes to be as metal. So silver ions would want to become silver metal. All right, that means that would be a reduction. That means that the opposite is going to be happening to the other metal. All right, so again, at the cathode, which is where the reduction happens, we're showing the silver ions becoming silver metal. At the anode, we've got nickel metal becoming nickel ions. All right. Notice I had to for the half reaction, I had to multiply this by 2, so that your electrons would be the same in both the oxidation and the reduction half reactions. All right, I'm not going to stress this that much, but it also has to label things as positive and negative. Just remember that the anode is going to be the negative, and a way to remember that is a negative ode. In the same way, anion, you can say a negative ion. Anode, you can say a negative ode, and that would remind you that that's negative. And just like with cation, you can think of the T as being a big plus, because the T kind of looks like a plus. That's a way to remember that that would be the plus when you label this cell. All right, which way would the electrons flow? Well, if it's the nickel anode, which is losing electrons, then the electrons are going to flow from that over to the silver. Right, so nickel to silver. And if you think about what is happening at the silver, so if things are flowing towards the silver electrode, the silver one is going to be where the electrons are coming in to the half cell, so that if the electrons are coming in there, the cations, which are the positive ions, are going to move towards that silver ion, and the anions in the solution would be moving towards the nickel. All right. So in 2014, the question that's asked, they give you essentially the strategy is that they give you a cell electromotive force, and they ask you to figure out what the electromotive force is on, or like what the standard reduction or oxidation potential is for one of the half reactions. All right. So a way to think about this, well, when you look at the balanced reaction, which they provide in the textbook, all right, we can break it up into an oxidation half reaction and a reduction half reaction. All right. And so only one of these is given in the appendix of your textbook. If you are using your data guide, we could probably, let me see, do they have cadmium here? I don't think that they have that. They actually have more of these listed in the textbook than in your data booklet. But this would be the standard EMF oxidation with the hydrogen electrode for that reaction right there. And the way that we get to it is that what is actually listed in the appendix is this reaction right here. All right. So remember that in these tables they show everything as a reduction. All right. And this would be the electromotive force for that. All right. And so what this means is that if you did this reaction with a hydrogen electrode, all right, this would actually not occur. All right, because that's a negative. All right, for this reaction to occur with the hydrogen electrode, these things right here need to be positive. So if we wanted to figure out what the standard oxidation potential of this thing would be relative to that hydrogen electrode, all we have to do is change it to change this to oxidation. All right. And then just change the sign of this. All right. So, we don't know what the standard reduction potential of this guy is right here. But what we know is that the electromotive standard electromotive force for the cell is going to be the one for the oxidation plus the one for the reduction. And the problem gives us the one for the entire cell. We figured out what the one for the oxidation is by doing this little part up here. And all we have to do is calculate what it would be for the standard reduction potential for this half reaction. And this is what it would calculate out to be. All right, so if we're going to do a little sketch of this, notice that the cadmium is the one that's being oxidized. All right, so we want to show that right there as being the anode. All right. And since it's being oxidized, it's losing electrons. The electrons are going to be going this way. All right. The palladium is going to be the cathode. All right. And one thing that's interesting about this, it's arguable about whether palladium is an inert electrode here. Normally, when we talked about inert electrodes, we said that palladium is one of the common electrodes. But notice that you're actually going to be plating palladium atoms on this because that's what happens when this material right here gets reduced. All right. So anyways, the electrons are going this way, and what this would register right here is plus 1.03 volts because that was what the voltage was of the entire cell. All right. So one thing I want to point out about this is in order for this to be the voltage. Notice that it's got this little degree mark right there. And what that means is that this is conducted under standard conditions. All right. So in order for this to be the actual voltage that you would get, remember, you would have to have 1 molar concentration of cadmium ions here and 1 molar concentration of these, I guess that would be palladium tetrachloride ions in this solution right here. All right. Okay, so if there's any of these homework problems that you definitely, if you're going to learn how to do any of these, I would say that 2016 is probably the most important. It's the type where you're taking information straight from the data booklet and you're calculating a voltage. All right, so taking a look at the balanced reaction, this is 2016A. Hopefully you can break that apart into 2 separate half reactions. All right, this would be the oxidation half reaction. Here's the reduction. And what we want to do is give the standard oxidation potential and the standard hydrogen electrode reduction potential for those 2 different half reactions. All right, so since this is, so notice when they write these in the data booklets, everything is always written as the reduction. All right. So for the half reaction that you have that is written as the reduction, all right, so this is the one that's the reduction, the number that you're going to get should be exactly what it says in the data booklet, or in this case, I got this from the appendix of the textbook. All right. So what that means is that for the oxidation, we can still do it. You just need to remember that it needs to be turned around. So let's see, is that in, my guess is that's probably in there. Aluminum, all right, yeah. So here you can see that aluminum is written as a reduction, and this is its standard potential. So if you write this reaction reversed as the oxidation, all that does is it changes the sign. All right, so that's why that's a positive 1.66, and we know that the electromotive force of the cell is going to be the sum of these two. All right, so we just take these two things, add them up, and get this right here. All right, so notice one thing about this, just following your sig fig rules, since this is an addition subtraction operation, you should round it at that appropriate position. All right, in the next reaction, again, breaking things up into an oxidation and a reduction reaction. One thing I want to point out about this is that notice in order to get that this right here is not a fully simplified reaction, but it is the appropriate half reaction because it is the oxidation half reaction that accompanies this reduction half reaction. And we want to have it so that the number of electrons in one match the number of electrons in the other. All right, so the one thing about this is that it does not change the amount here. Just because you double this reaction does not mean that you double the electromotive force. All right, so this is iron 2 going to iron 3, and let's see, iron 2, let me see, is that in this particular, okay, iron 2 and iron 3. All right, that is, notice this is plus 0.77. All right, so, and that would be as a reduction. So if you are writing it as an oxidation, you show it as the opposite. All right, the reason that this is not is slightly different from this one right here is I got the data from the appendix in the textbook rather than the data booklet. So this is your reduction, and that would be written exactly the way it is in the booklets because it's a reduction, and that's how those are written. All right, so the electromotive force of the cell is just the sum of those two things, and this is what you get. So I can, in this particular case, I can round out here because of these values right here. Note that if you had used the value from the data booklet, you would have to round it at a different place because of sig vig rules. Okay, so the last problem just gives you a bunch of half reactions, and it asks you to design a cell that would either have the highest electromotive force, in other words, way of saying that is the highest voltage, and the other being the lowest voltage. All right. So one thing to remember about this is that in order for something to work, the cell to work, it's got to be positive. All right. If you calculated something and it were negative, essentially what it would mean is it would work in the opposite direction. All right. So we want to write these reactions in the direction that they would actually occur. So we're looking, in terms of the biggest, you want to find the highest positive force that you can find. All right. So the way I'm looking at this is I'm trying to look at these. So for any given reaction here, remember that it's opposite. Like if I wanted to draw this as an oxidation instead of a reduction, all I'd have to do is change the sign. So I've just kind of drawn some numbers out here, and I'm trying to figure out what would give me the, remember I've got to pick one from this column and one from this column because one of them's got to be a reduction and one's got to be an oxidation. All right. So if I take this guy right here as a reduction, let's see which one of these other things could I have that would give me, that I could have as an oxidation. All right. And so if I drew this guy right here as an oxidation, this would be its electromotive force, and I believe that these two numbers right here would give me the biggest number. All right, so that's what I do right here. All right, so to get the smallest one, I'm going to look here and see, and the ones that I'm finding are this guy right here plus this guy right here. So notice in both cases you found one of the numbers from as written, and the other number has to come from the opposite. And that's the answer that you'd get.